Welcome back to Calculus Universalis. Today's topic is a must-know for the AP exam, optimization problems, where you apply derivatives to maximize or minimize something in real-world scenarios. Let's start with this. Optimization strategy. A optimization problem will ask, what's the minimum or maximum value of something? That something could be area, volume, cost, distance, anything. So the first step is read the problem carefully. Now this is a a must-do, easy brainer, but it can lead to many mistakes. Now we're just going to roll right through these. 2. Write equation for the objective function. Now, what does this mean? It means write the equation that it's based on. If it's talking about maximizing the area of a cone, write the formula for a cone, air volume of a cone, whatever it's asking for. Write the equation out, and then you can use that to build upon it. Number 3, I'll just read these. Use constraints in the problem to reduce the objective function to one variable. 4. Take the derivative of the objective function. 5. Find critical points. 6. Use a sign chart. And 7. Enter in a sentence and include units. So these are the most important thing. Units will definitely get you on the AP exam. But let's hop right into an example and see how they do it. So example number 1. Let's say a farmer has a river, and on this river he wants to make one of these things, a rectangular area. He only needs to fence 3 of the sides, obviously, not along the river, and he has 100 meters of fencing. So total perimeter length, so this is going to be the width, and then this will be the length. Okay. And then we know x plus y is going to equal 100. So which dimensions will give the maximum area? How do we find this? Well, we have a constraint. This is our constraint. This must be true. So basically, we need to write another formula. Area equals x times y. This is what we want to maximize. So we have the constraint. We're going to plug the constraint into the formula, which is y equals 100 minus 2x. Plug that in for this, and you get basically area equals 100 minus 2x times x, because this became the y. You multiply everything out, and you get maximum area is 100 minus 2x squared. And then we take the derivative of this function and set it equal to 0. So a prime x equals negative 4x. Sorry, and then the x should also be multiplied out here. Plus 100. Set equal to 0. 0 equals 100 minus 4x. When you solve for x, you get x equals 50. Or sorry, you get 25 for x. And then you go ahead and plug this back in to your original equation, your constraint. So it's 50 plus y equals 100. So y must be 50, because you have 25, 25. See, the maximum dimensions are 25 by 50. And this is x and this is y. So that's your answer. You find your dimensions, and then to find maximum area, you just multiply them out and see what it gets you. But that's how you find it. Let's do one or two more problems. Our next problem is going to be an open top box. This is a classic. So you're going to draw yourself. And drawing the image is going to help you a lot in all these problems. We have an open top box. And you're doing this by cutting squares in a 12 by 12. Like this. I really don't like these ones. So it's 12 by 12, I guess, square. I filled up the sides, which cutout gives the maximum volume. Let x equal the side length. So the length is 12 minus 2x. Width 12 minus 2x. Height equals x. Right, because this is an x, an x. The side that you cut out, we're labeling x, and you know this is 12, so 12 minus 2x is the length of this side. And then what you do is you just put the volume formula, multiply them all together. It's 12 minus 2x squared times x. And then you're going to take this derivative, set the function equal to 0, and then I'll just speed through it pretty quickly. When you do this, you get a domain of x equals 0 or 6, and it must be in between there basically, but you have to check the endpoints. So we plug in 0 and we plug in 6, and we figure out that x equals 2 gives the maximum volume, which is what we found from setting this equal to 0. And these are just our endpoints for domain, because it can't be more than 6. Plugged them all in, and then we get 8 by 8 by 2 by 2, and that's our maximum volume of the box. Thank you for watching. But here's an optimization playbook that you can go by the next time you do one of these problems. I'll give you a quick review of the video, and then you can be off on your way studying for your next test. So we're going to identify what to maximize or minimize. Then we're going to write an objective function, use the constraint to reduce one variable, differentiate such derivatives to 0, answer with units and clear explanation, and then go ahead and practice on your own. Next video we'll do related rates, which is one of the most dynamic types of problem in calculus. Make sure you subscribe, and I'll see you in the final video of Unit 5.